Hey everyone, so today we're looking at the blue reaction mechanism where a phosphate group right here is transferred from carbon 5 to carbon 4, and then the OH on carbon 4 is transferred to carbon 5, as you can see in the final product. And so to decipher the entire mechanism, we are given four clues right here, and these clues essentially just tell us how the mechanism works and tells us certain reasons why certain things are nucleophiles or electrophiles, etc. So the first clue is that the addition of a metal chelator, EDTA, decreases binding but does not affect the turnover rate. So this clue essentially tells us that a metal ion cofactor, something like Mg2 plus, is used here for the catalytic strategy of both proximity and orientation. So that's what you can see right here with the Mg2 plus. Um, and essentially it just anchors the negative charge on the phosphate group in the active site. So the second clue that we can see here is that the phosphate group retains stereochemistry from reactant to product, and this essentially tells us that it proceeds via a double displacement or a ping pong mechanism, all in all just requiring two sequential nucleophilic attacks and additionally just implying the strategy of covalent catalysis. So the third hint is that a catalytic triad was found to be responsible for the enzyme's catalytic activity, and that the loss of histidine 98 resulted in 45% activity, loss of tyrosine 47 resulted in 30% activity, and the loss of serine 23 resulted in 15% activity. So this tells us that the loss of serine 23 drops the activity to 15%, while the loss of histidine 98 and tyrosine 47 also impacts the reaction a lot. This overall just indicates that it is a modified catalytic triad where serine 23 acts as the main nucleophile, and then histidine 98 acts as the general base, and tyrosine 47 stabilizes histidine 98. So the final hint is that histidine 102 was also found to be required for full catalytic activity. However, the pK of the residue was measured to be 8.2. Now, what this tells us is that histidine 102 has an elevated pKa of 8.2, meaning that it is protonated at physiological pH, and it will act as the general acid in our first step. And overall, this highlights the use of histidine in a catalytic strategy of general acid or base catalysis. So for our initial bond forming step, the oxygen on serine 23 is going to be our nucleophile. So let's label that. And the phosphorus atom on the C5 phosphate is going to be our electrophile. So on its own, the serine hydroxyl group is only a moderate nucleophile, but since it's activated by our catalytic triad, histidine 98 acts as a general base to pull the hydrogen away. This overall just shifts the entire electron density onto the serine 23 oxygen, all in all creating a highly reactive species of an O minus. And then after that, we can justify the electrophile's reactivity by looking at the resonance structure of the phosphate group. So here we can see that it resonates like this, right? It can also resonate like, let's make that more clear, like this, right? Overall, just making the central phosphorus atom positive, as you can see right there. The negative oxygens pull the electron density away from the central phosphorus atom, and it gives it a strong positive partial charge. So the dipole would be written like this, and overall just makes it highly susceptible to attack. To get into the meat of the mechanism, let's start off with the mechanism. So the first thing that happens is the unprotonated nitrogen on the histidine 98 acts as a general base, and it grabs the proton from the serine 23. Now, the electrons from the OH bond now attack the electrophilic phosphorus. So goes up here, attacking this. And then to avoid the phosphorus atom from exceeding the octet rule, the bond connecting the phosphorus atom to the double bond O breaks and it pulls electrons to the oxygen. And then those same electrons come down and reform the double bond. So you can write it coming down like this. And then this essentially kicks off our leaving group. So that'll be this oxygen right there. And it breaks the bond between the phosphorus and the C5 oxygen. Finally, essentially what happens is that anion from the oxygen that just got formed attacks our histidine 102 hydrogen and it acts as a base to grab a proton from our protonated acid, which is histidine 102. So now we can see the new intermediate, which is right here, as a result of the previous reactions. In this new intermediate, notice that the Mg2 plus ion stays coordinated with the phosphate group and it now stabilizes the negative charges on the serine 23 intermediate. Additionally, the substrate has shifted so that the carbon 4 hydroxyl group, so right here, this hydroxyl group, is now positioned near the phosphates. And essentially, this is because now the roles reverse. So now you can see histidine 102, and this is what I mean by the roles reversed. The electrons from the nitrogen attack the hydrogen on the carbon 4 hydroxyl and it deprotonates the carbon 4 hydroxyl group. And now the oxygen on the carbon 4 acts as our second nucleophile, attacking the phosphorus. So it attacks the phosphorus, and just like before, the phosphorus and oxygen double bond break, and then they reform. And then this essentially it breaks the bond connecting the phosphorus to the serine 23 residue, and then the oxygen from the serine 23 residue now comes over here and grabs the proton from the histidine 98 residue, where the serine 23 residue and the electrons from the oxygen that are attacking the hydrogen acts as the base, and then the hydrogen on the histidine 98 residue attached to the nitrogen acts as the general acid. So here we see the final products of the reaction and the final enzyme right here. And then this product right here of the substrate, which matches what we were looking for, the phosphate group on the carbon 4, as well as the OH on the carbon 5, which we can see right here. I also think that it's very important to note that the magnesium 2 plus is now next to the phosphate attached to the carbon 4, stabilizing those negative charges on the phosphate, as well as the fact that the nitrogen from histidine 102 now being protonated again just because of the environment. And so overall, this would be the initial part of the reaction, or the first step. This would be the intermediate, and then this would be our final products. And all in all, the second displacement just breaks the covalent intermediate and restores the enzyme right here back to its original state. So these two would be similar. And we also see the retained stereochemistry right here due to the double displacement, from the first displacement inverting the stereochemistry, and then the second displacement inverting the stereochemistry back. All in all, these would be the products, and thank you for watching.